In this video, we will practice working with logistic equations, and we will use them to solve some real-world problems. This is a BC only topic. If you have not yet watched the introductory lesson, you should definitely watch that first. This video will make a lot more sense if you do. You can either click the link in the upper right-hand corner or find the link in the description. In the introductory lesson, we learned that logistic growth eventually levels out, as compared with exponential growth, which increases faster and faster forever. The upper limit of a logistic growth curve is called the carrying capacity, and it is represented by the letter L. Logistic growth is often a better model for growth in the real world. A population doesn't tend to grow faster and faster forever. Instead, it usually levels off after a while. A given forest can only support so many bears. A given lake can only support so many fish. Also, when you were first conceived, you grew exponentially at first, but after a while, your growth leveled off. We learned that this is the differential equation that models logistic growth, and this is its solution. I want you to memorize both of these equations. We learned that the value of k controls whether the graph is increasing or decreasing. If k is greater than 0, the graph is increasing. If it's less than 0, the graph is decreasing. As I mentioned, the carrying capacity L represents the upper limit of the graph. A logistic growth curve has a point of inflection where the graph goes from concave up to concave down. The point of inflection is at a y value that is half of the carrying capacity. The b value tells us something about the horizontal position of the point of inflection. If b equals 1, the point of inflection is right on the y-axis. If b is greater than 1, the point of inflection is shifted to the right. And if b is between 0 and 1, like say 2/3, then the point of inflection is shifted to the left. Notice you can't have a negative b value. We also learned that the fastest growth, or decay, occurs at the point of inflection. For exercises 47 through 50, we need to match these four logistic equations to each of the four graphs above. Just to review, the number in the numerator is the L value, the carrying capacity. The number in front of E is the B value. And the number in front of the x is the k value. Remember that in the model, there's a negative sign in front of the k. So in this case, k is just 2, not negative 2. You can basically think of it as the opposite of what you see here. So if this was a positive 2, then k would be negative 2. All four equations have an L value of 12, so that's not going to help us. But just as a review, this 12 means that the upper limit of each graph should be 12, and we can see that in each case that is true. The equations do not all have the same b value, so let's talk about that. For number 47, b is equal to 1 because there's no number visible in front of the e. For number 48, b is 3. For number 49, b is 1/2. And for number 50, b is equal to 1, just like number 47. Remember, the b value tells us whether the point of inflection will be shifted to the right or to the left, or if it's right on the y-axis. If b is equal to 1, that means the point of inflection is right on the y-axis. So let's see. All four graphs have an upper limit of 12, so the point of inflection will occur at a y value of 6. For graphs C and D, we see that the point of inflection is right on the y-axis. That means for these graphs, the b value is 1, just like we see in number 47 and number 50. So we've narrowed it down to 47 and 50 will be either C or D. Number 48 has a b value that's bigger than 1. That means the point of inflection should be shifted to the right. Number 49 has a b value that's between 0 and 1. That means the point of inflection should be shifted to the left. So let's look up and see. Graph A has a point of inflection that is shifted to the right. just like we would see for a b value of 3. That means this must be the graph that corresponds to number 48. Graph B has a point of inflection that is shifted to the left. That's what we would see if we had a b value of 1/2. That means this must be the graph of number 49. We can use the k value to figure out which equation goes with which graph. For number 47, the k value is 1. There's no visible number in front of the x, so it must be a 1. For number 50, the k value is 2. The k value controls whether the graph is increasing or decreasing. Since both k values are positive, we see that both graphs are increasing. But the k value also tells us how steep the graph is. So a graph with a k value of 2 should be steeper than a graph with a k value of 1. So which of these graphs is a little bit steeper than the other? Graph C is steeper. So that means this must be number 50. So that's it for the matching. In the following exercise, the logistic equation models the growth of a population. Use the equation to A, find the value of k. K is going to be the number right here, not including the negative sign. So k is 0.2. B, find the carrying capacity. The carrying capacity is right here. So L equals 5,000. Now C, find the initial population. The initial population is the population at time t equals 0. P at 0 equals 5,000 over 1 plus 39, because if t is 0, we have e to the 0, which is 1. Obviously 1 plus 39 is 40. So the initial population equals 125. Part D. Determine when the population will reach 50% of its carrying capacity. In this case, the carrying capacity is 5,000. So we are looking for the time when the population will reach half of this. In other words, for what time t will P of t equal 2,500? We need to set our expression for P of t equal to 2,500 and solve. Here's a useful algebraic shortcut. When you have a fraction equal to a number, you can swap the denominator with the number out here by itself and still have a valid equation. So let's do that now. Kabam! Of course, 5,000 divided by 2,500 is 2. On the next step, we will subtract 1 from both sides. Then we can divide both sides by 39. To get rid of the base e, let's take the natural log of both sides of this equation. Natural log and base e cancel each other out. So on the right-hand side, we will be left with negative 0.2t. I'm thinking ahead, so to help me simplify later, I'd like to rewrite 1 over 39 as 39 to the negative 1 power. A property of logarithms says that if you take the log of something with an exponent, you're allowed to take the exponent and move it out to the front. So this would be the same as negative natural log 39 is equal to negative 0.2t. Dividing both sides by negative 0.2 gives us t equals natural log 39 over 0.2. And if you don't have access to a calculator, then this is the final answer. If this shows up on the calculator active part of the test, you'll put t equals 18.318. Part E. Write a logistic differential equation that has the solution P of t. Here is the logistic differential equation that we memorized. Using t and p instead of x and y, the differential logistic equation becomes this. Substituting 0.2 for k and 5,000 for L gives us the final answer. In the following exercise, the logistic differential equation models the growth rate of a population. Use the equation to A, find the value of k. Here is the memorized model for the logistic differential equation. To make this problem match the model, we need to factor out 0.1p. When you factor out 0.1p, you divide each term by 0.1p to figure out what goes inside the parentheses. 0.1p divided by 0.1p is 1. And then p squared divided by p is p. And 0.0004 divided by 0.1 is 0.004. Let's rewrite 0.004 as a fraction to make it look more like the model. In elementary school, we learned that 0.004 is the same as 4 thousandths. So for a split second, we have this. But 4 goes into 1,000 250 times. So reducing the fraction gives us this. Comparing with the model, we see that k is 0.1 and L is 250. That answers part A and part B. The value of k is 0.1 and the carrying capacity is 250. That just leaves part C. Determine the value of p at which the population growth rate is the greatest. In the introductory lesson, we learned this key fact. The fastest growth rate occurs at the point of inflection, which in turn has a y value that is half of the carrying capacity L. We are using p instead of y, so the fastest growth will occur when p is half of the carrying capacity. So the growth rate will be the fastest when p is equal to 125. For the following problems, we need to find the logistic equation that passes through the given point. For number 56, comparing the differential equation to the memorized model, we can tell that k is 2.8 and L is 10. This is the memorized model for the solution to a differential equation. Let's substitute 2.8 for k and 10 for L. So now we have this. To finish off the solution, we just need to find the value of b. We can find it using the initial condition 0, 7. When t is 0, y is 7. That gives us 7 equals 10 over 1 plus b, because when t is 0, we have e to the 0, which is just 1. When you have a number equal to a fraction, you are allowed to swap the denominator and the number by itself. So that gives us 1 plus b is equal to 10 over 7. Subtracting 1 from both sides, we have b is equal to 10 over 7 minus 1. But instead of 1, I'm going to put 7 over 7. So b is equal to 3 over 7. Substituting 3 over 7 in for b gives us the final answer. Number 58. To make this differential equation match the memorized model, we need to factor out 3y over 20. When you factor out 3 over 20y, you divide each term by 3 over 20y. Dividing 3y over 20 by 3y over 20 gives you 1. When you divide y squared by y, you get y. But how do you divide by 3 over 20? Well, dividing a fraction by a number is the same as putting that number in the denominator. So if I want to divide by 3 over 20, I can just put 3 over 20 in the denominator. So what is 1,600 times 3 over 20? 240. Comparing to the model, we can see that k is 3 over 20 and L is 240. This is the memorized solution for a logistic differential equation. Substituting 3 over 20 for k and 240 for L gives us this. To finish off the solution, we just need to find the value of b. To find it, we can use the initial condition 0, 15. When t is equal to 0, y is 15. So we get 15 equals 240 over 1 plus b, because when t is 0, we have e to the 0, which is 1. A very useful algebraic shortcut is that when you have a number equal to a fraction, you're allowed to swap the denominator with the number over by itself. So we get 1 plus b is equal to 240 over 15. That's 16. Subtracting 1 from both sides gives us b equals 15. Substituting 15 back in for b gives us the final answer. Number 60. At time t equals 0, a bacterial culture weighs 1 gram. 2 hours later, the culture weighs 4 grams. The maximum weight of the culture is 20 grams. Logistic growth. Part A. Write a logistic equation that models the weight of the bacterial culture. At t equals 0, a bacterial culture weighs 1 gram. This statement gives us the initial point 0, 1. 2 hours later, the culture weighs 4 grams. This gives us another point, 2, 4. When they tell us that the maximum weight of the culture is 20 grams, they are telling us that the carrying capacity L is 20. Part A. Write a logistic equation that models the weight of the bacterial culture. Here's the memorized model of a logistic equation, and we know that L is 20. So we start with this. We just need to find B and K. Let's plug in our first initial condition and see what we get. When t is 0, y is 1. We get 1 equals 20 over 1 plus b, because when t is 0, we have e to the 0, which is just 1. When you have a fraction equal to a number, you can swap the denominator with the number. That gives us 1 plus b equals 20, and subtracting 1 from both sides, we get b equals 19. Putting 19 in for b gives us this. Now let's use the other point we were given and see what happens. When t is 2, y is 4. That gives us this equation. Now we can swap the denominator with the 4. 20 divided by 4 is 5, so we have this. Subtracting 1 from both sides, we have this. And dividing both sides by 19 gives us this. We need to get rid of this base e, and we can do that by taking the natural log of both sides of the equation. For a brief moment we have this, but the natural log and the base e cancel each other out, so we will be left with negative 2k on the left side of the equation. So now we have this. Let's divide both sides by negative 2. So k equals natural log 4 over 19 divided by negative 2, which is the same as negative 1/2 natural log 4 over 19. We could leave it like this, but the rest of the problem will be easier if we simplify using properties of logarithms. For example, we have learned that when you have a number in the front, you can move it to the exponent position without changing the value of the expression. In this case, I'm going to leave the negative sign where it is, so I'm just moving the 1/2. So now we have k equals negative natural log of 4 over 19 to the 1/2 power, and we know that the 1/2 power is the same as square root. The square root of 4 over 19 is 2 over radical 19, so this is the value of k. Let's substitute this back into the equation to complete the solution. Notice that we already have a negative sign in front of the k. Minus a negative is a positive, so we're going to be left with a positive right here. This is perfectly acceptable for the final answer, but we are going to need this equation to answer the other parts of this problem. So I would like to simplify a little bit. I see that we have the base e and then the natural log. These will cancel each other out, but you have to separate the t away from it with some parentheses. Please understand that this t is an exponent. So the base e and the natural log will cancel each other out, but you will be left with 2 over radical 19 to the t power. So this is the equation that models the weight of the bacterial culture. Part B. Find the culture's weight after 5 hours. Let's use the equation we just found. All we have to do is substitute 5 for t. If you don't have access to a calculator, then this is the final answer. If this shows up on the calculator active part of the test, then you type it in. So we type 20 and we hit alpha y equals enter to get a nice fraction. And then it's 1 plus 19 times. We need another fraction here, so I will hit 2 and then alpha y equals enter. And we need radical 19. So radical 19. And this fraction is being raised to the 5th power. So close the parentheses and raise it to the 5th power, and that's it. This is more meaningful as a decimal, so let's go with 14.426. This is the weight of the culture after 5 hours. Part C. When will the culture's weight reach 18 grams? The equation we found in Part A gives the weight of the culture at time t, so we need to set this expression equal to 18 and solve for t. We can swap the denominator with the 18. So now we have this. On the next step, I'm going to reduce the fraction to 10 over 9 and subtract 1 from both sides. I'm subtracting 1 here, but instead of writing 1, I wrote 9 over 9. So you can easily see that 10 over 9 minus 9 over 9 is 1 over 9. Remember, we are trying to solve for t. The next step is to divide both sides of the equation by 19. You can divide a fraction by 19 by multiplying the denominator by 19. That's 171. To eventually get t out of the exponent, we need to take the natural log of both sides of this equation. Now, using the properties of logarithms, we can take the t and move it out to the front. Finally, to get t by itself, we divide both sides by natural log 2 over radical 19. This is very ugly, but if you do not have access to a calculator, this is the final answer. If you do have access to a calculator, you get t equals 6.599 hours if you truncate, or t equals 6.600 hours if you round. Part D. Write a logistic differential equation that models the growth rate of the culture's weight. Here is the memorized model for a logistic differential equation. Remember that in Part A we found that L was 20 and K was negative natural log 2 over radical 19. So dy dt is equal to this. That's the answer to the first part of the question. But then it goes on. Repeat Part B using Euler's method with a step size of h equals 1. Compare the approximation with the exact answer. Part B was to find the culture's weight after 5 hours. In other words, y at 5. So now we need to find y at 5 again, but this time using Euler's method with a step size of h equals 1. That means that delta t is equal to 1. For Euler's method, we need at least one initial point. In the setup of the problem, we were given 2 points, 0, 1 and 2, 4. I covered Euler's method in a previous video, so if you're not familiar with it, you should watch that video first. You can either click the link that appears in the upper right hand corner or find the link in the description. Euler's method involves making a table, and the top row shows what you're going to put in each column. Memorize this setup. We are going to use the point 2, 4 instead of the point 0, 1 because the x value of 2 is closer to the target x value of 5. You put your initial point in for t and y right here. We can find the rest of the values of t using delta t, which is the change in t from one row to the next. Delta t is 1, so adding 1 each time gives us 3, 4, and 5. We need delta y to find the next y value, but first we need dy dt, which is given by this equation. This is sufficiently complex that I'm going to type it in as a function on my calculator. So go to your calculator and hit y equals. I'm going to type it in as y2. I have typed the equation in as y2, but the calculator will not let me use a y variable, so I had to use an x here and here. Before we go on, I need you to adjust one feature of your calculator. Hit Second Window to access the Table Setup menu. Go down to where it says Independent. If your calculator has Auto selected, I want you to change it to Ask. After that, you can hit Second Graph to access the table. This might be a tiny bit confusing because it says X, but remember this is really a Y. So we can put in any value of Y and it will give us the value of the equation we typed in y2, which in this case is dy dt. For the first row, y is 4, so I'm going to type in 4 and the calculator will give me dy dt. And there it is. We are going to need more decimals than this, so let's move the highlighter over to here and we get as many decimals as we need. I think I'm going to use 7 decimal places. So here's my first dy dt. Next I need to find delta y, which I find by multiplying dy dt by delta t. Luckily delta t is only 1, so multiplying by 1 won't actually change this number. This is the change in y. We can find the next y value by adding delta y to the previous y value. To find the next dy dt, we need to type this ugly number into the calculator. There it is! Kabam! So this is the next dy dt. Let's copy down 7 digits. So there's dy dt. Again, normally we find delta y by multiplying dy dt by delta t, but multiplying by 1 changes nothing, so I'm just going to copy it over. This is the change in y, so we can find the next y value by adding delta y to the previous y value. Now we repeat the process one more time. To find the next dy dt, we need to type this number into the calculator. So there it is. Kabam! This is dy dt. Let's write down 7 digits. So here is our dy dt, and multiplying by a delta t of 1 gives us the same value for delta y. This is the change in y. So if we add delta y to the previous y value, we get the last y value. This is our approximation for the weight of the culture after 5 hours. We need to compare this approximation with the exact answer. In part B, we found the exact answer was 14.426 grams. The approximation of 13.804 grams is a bit less than the exact answer of 14.426 grams from part B. Part E. At what time is the culture's weight increasing most rapidly? Explain. We have learned that the fastest growth occurs at the point of inflection, and the point of inflection has a y value that is half of the carrying capacity. So the fastest growth occurs when y is equal to L over 2, which in this case is 20 over 2, which equals 10. This is the weight of the culture at time t that we found in part A. We need to set this expression equal to 10 and solve for t. Next we can swap the denominator with the 10. Now let's subtract 1 from both sides. Next we divide both sides by 19. To get t by itself, we start by taking the natural log of both sides of this equation. Now we can use the properties of logarithms to move this exponent of t out to the front. Finally, we can get t by itself by dividing both sides of the equation by natural log 2 over radical 19. And if you don't have access to a calculator, this is your final answer. If you do have access to a calculator, you can say the fastest growth occurs after 3.779 hours. However, if this problem is calculator active, you didn't actually have to do any of this work. So let me show you how you can find this answer using your graphing calculator. Let's start by typing this into the calculator as y1. Of course, I had to put the x power instead of the t power. We want to know when this equation reaches a value of 10. So let's type y equals 10 for y2. Essentially, we need to find the intersection between these two graphs. Zoom 6 gives you a 10 by 10 window. So this is cutting it a bit close because y equals 10 is right at the upper edge of the screen. I'm going to adjust the window a little bit. Let's let y max be 15. To find the intersection point, we hit second trace and choose option 5, intersect. Move the pointer close to the point of intersection and then hit enter 3 times. Enter, enter, enter. So there's the answer, 3.779, which is the same thing we got the long way.